Now we are going to another important result, that is the theorem states that the k conjugate of alpha. What is k conjugate? We know that k conjugate of alpha is sigma I of alpha, where I ranges from 1 to n. Sigma I of alpha, this is k conjugate of alpha, where I ranges from 1 to n. Sigma I of alpha, this is the k conjugate of alpha. So, the k conjugate of alpha are the zeros of p alpha in C. Each are repeated n by m times. Sigma I alpha, k conjugate of alpha, that is sigma I alpha. Then sigma I alpha, this sigma I alpha are the zeros of p alpha. What is p alpha? In C. P alpha means the minimal polynomial in C. Okay. So, if k conjugate of alpha, that is sigma I alpha, where I ranges from 1 to n, are the zeros of p alpha in C, each are repeated n by m times. N by m times, where what is n? N is the degree of this minimal polynomial, means degree of p alpha. N equals degree of p alpha. So, m equals, not n, sorry, m be the degree of p alpha and n be the degree of the number field, is a divisor of n. This is our another theorem. K conjugate. What is k conjugate of alpha? We know that it is given by sigma I alpha, and sigma I alpha equals alpha I, whatever may be, are the zeros of this minimal polynomial p alpha in C. Each repeated n by m times, where m be the degree of p alpha, that is the divisor of n. What is n? N be the degree of the number field. How to prove this one? So this is again depends upon the definition of definition of the field polynomial and the previous theorem. So we know that the field polynomial, what is field polynomial? We know that f alpha t is product I ranges from 1 to n t minus sigma I alpha. And it is given the sigma I alpha, that are the k conjugate of alpha, which are the zeros of the given minimal polynomial p alpha. Also by previous theorem, we know that the field polynomial is nothing but the power of the minimal polynomial. This is from the previous result, that is the field polynomial is nothing but the power of the minimal polynomial, that is p alpha, sorry, f alpha is p alpha power s. Okay, mark it as an equation 1. So, what is sigma I alpha? According to the hypothesis, sigma I alpha are the zeros of p alpha. Sigma I alpha are the k conjugate of alpha. Sigma I alpha means k conjugate of alpha, which are the zero of p alpha. So that means this product I ranges from 1 to n t minus sigma I alpha equals p alpha power s of t. Okay, f alpha is p alpha power s, and the sigma I alpha, that is the conjugate of alpha, are the zeros of p alpha in C. That means, according to this argument, product I ranges from 1 to n t minus sigma I of alpha is nothing but p alpha power s of t by this argument. Agreed? Okay. Hence, what is p alpha power s of sigma I alpha? P alpha power s of sigma I alpha is nothing but p alpha of sigma I alpha all power s. P alpha of sigma I alpha all power s, that equals p alpha of s of t is this one. So it is product I ranges from 1 to n, t is replaced by sigma I alpha. So sigma I alpha minus sigma I alpha equals 0 itself. That means P alpha sigma I alpha. P alpha of sigma I alpha all power s equals 0. That means P of P alpha of sigma I alpha equals 0. So that means this sigma I alpha be the 0 of minimal polynomial P alpha. This is our first one. Okay. Sigma I alpha be the 0 of P alpha in C. So here f alpha t is defined as in this way. F alpha is nothing but P alpha power s. That is our previous theorem. So according to this argument, product I ranges from 1 to n t minus sigma I alpha equals f alpha of t means P alpha s of t. Okay. Hence P alpha power s of sigma I alpha is nothing but P alpha of sigma I alpha all power s. That is product I ranges from 1 to n, sigma I alpha minus sigma I alpha, that becomes 0. Agreed. So that means P alpha of sigma I alpha equals 0. That means sigma I alpha are the roots of the minimal polynomial P alpha. So finished. Now let degree of P alpha. The degree of P alpha is m. So a divisor of n, this given, it is a divisor of n. Degree of P alpha is a divisor of n, where n be the degree of the number field, then clearly these roots are repeated n by m times. Okay, so why? Because n be the degree of the number field and m be the degree of this P alpha, and this m be a divisor of n, therefore these roots are repeats n by m times. Enough. So these are the two important results. Agree. That is, field polynomial is defined as f alpha of t equals product I ranges from 1 to n t minus sigma I of alpha, and we know that every field polynomial can be expressed as the power of minimal polynomial, and this minimal polynomial P alpha has, if sigma I alpha be the k conjugate, then that P alpha has distinct or zeros of the polynomial P alpha, minimal polynomial P alpha, and they are repeated n by m times. Okay. Now we are going to another important concept, that is discriminant. What is the discriminant? So, come to the definition. Let k equals q theta. K equals q theta be a number field. And so what is degree? With the degree of k equals n. Okay. Let set alpha 1, alpha 2, etc. alpha n be the basis of k. K be a number field, means it is a vector space over k. Let alpha 1, alpha 2, etc. alpha n be a basis of k, since it's a vector field over k. Then the discriminant of the basis. The discriminant of the basis is defined as capital letter delta. It is delta of alpha 1, alpha 2, etc. alpha n minus 1 alpha n equals, it is determinant, it is defined as determinant of sigma I alpha j whole square. So this is the discriminant. What is k? K be a number field of degree n. Then since it is a field, it is taken as a vector space over q. Vector space over q. Then let alpha 1, etc. alpha n be the basis of k. Dimension of k equals n. Okay. So it has a basis. Let alpha 1, alpha 2, etc. alpha n be a basis of k. Then the discriminant of this basis. The discriminant of this basis alpha 1, etc. alpha n is expressed as in this way. Capital letter delta of alpha 1, etc. alpha n, and is defined as, it is determinant sigma I alpha j whole square. if possible, suppose there exists another basis, beta 1 etc. beta n. Beta 1 etc. beta n be another basis of this one. Be another basis. Then we know that beta k equals some Cik into alpha. Cik into alpha j. Okay. Alpha 1 etc. alpha n are the basis. But if possible, there exists another basis beta 1 etc. beta n. Then we know that this beta I can be expressed as a linear combination of this one. Okay. So beta k equals Eik into alpha j. Beta k equals Eik into alpha j means, beta k equals linear combination, sigma I ranges from 1 to n, that is alpha 1 etc. alpha n be a basis. If possible, there exists another basis beta 1 etc. beta n, then this can be expressed as the linear combination of this one, that is beta k sigma I ranges from 1 to n Cik alpha j. What is Cik? This Cik is a rational number. Cik for in set of or q. That's a rational number. Then the discriminant of this basis beta 1 etc. beta n is defined as, it is determinant Cik whole square into determinant of alpha 1 etc. alpha. So these are the two important definitions. That is K be a number field. Now we just consider the vector space over Q. Then it has a basis alpha 1 etc. alpha n. Why? Because degree of K is n. Then the discriminant of this basis is denoted as this one, capital delta alpha 1 etc. alpha n, and is defined as, it is the determinant of sigma I alpha j whole square. Then if possible, there exists another basis beta 1 etc. beta n. Then this beta I can be expressed as a linear combination of these alpha i's, that is beta k sigma I ranges from 1 to n Cik alpha j, where Cik is a rational number. Why? Because the number field is defined over Q. Then the discriminant of the second basis delta of beta 1 etc. beta n is nothing but determinant is Eik whole square into discriminant of this alpha 1 etc. alpha. Agree? Okay.